Swayam Prabha. Digital India. Educated India.
Would find a little interesting. So the problem is like very practical. So you do this, all of you use this smartphones, devices. You click here, and then suddenly you find the region whether which you are, right? Then you sort of ask this question that I am at this GPS location, and tell me the restaurants nearby or movie halls nearby, right? Or academic institutes nearby. No? So, you can ask these queries, and in all these queries what you essentially want to do is when for example, we studied this computational geometry, this GPS thing, and if someone told me in the class that you will have a GPS which will give you the coordinate of where you are, I did not believe what he was saying. I thought that these are in the books and maybe they are somewhere, but but these days these things are very common, right? You sort of grow up with it. It's a matter, it's a completely different matter altogether that I don't get used to it, but theoretically at least I understand a part of what is going around. I will try to convey that to you. Okay. So, the problem is as follows. Think of this Voronoi diagram subdivision of the plane. So, this is kind of a subdivision of the plane where you have broken up the plane into some convex regions. There can be other kinds of subdivisions as well. So, I will when I talk of the problem today, I will talk of even a more general kind of framework which even would subsume your Voronoi diagram. So, essentially what you have is a planar subdivision where you have subdivided the plane into some convex regions, and you click somewhere and you want to know which subdivision you are in, right. So, think Voronoi diagrams. You click somewhere. So, when the GPS, what does it do? It gives you the coordinate, right, some xy coordinate of where you are, and this structure is there, possibly stored in some data structure, and you have to figure out quickly which cell you are in. Now, if you exhaustively search all cells to figure out in which cell this xy lies, then like you would not be happy, right. You are this kind of new generation and you are very impatient. If it takes linear time, you would be very unhappy. So, you have to give you something better, at least log n, let us see. So, this is the essence of the problem that we would be discussing today. So, the topic is like point location in a planar subdivision. That is what we would be studying today. Now, first let us look at so this is this So, all sort of subdivisions that can be represented in this form, which is a planar straight line graph, would be amenable to what I say from now on. So, a planar straight line graph is like a Voronoi diagram is a planar straight line graph. So, you have vertices, edges. So, you can store the structure as a graph where the edges are straight lines. So, I will talk of such a subdivision. Now, planar straight line graphs are essentially stored well by a data structure called DCEL, it stands for, I think the D is doubly connected edge list. So, let us see for a moment what this data structure is. So, if you have a subdivision, what are the basic structures that you have with you? Like think higher dimensions when Arijit was talking. No, you have 0 dimensional facet, 1 dimensional facets, 2 dimensional facets. So, you need to store them. So, let us talk of plane. So, what you have is points, 0 dimensional, edges, 1 dimensional, and you have faces. So, I have to store them in such a way that, mind you, it is a planar connected region. So, if I start from any point, be it inside the region or on the edges or on the vertices, I should be able to walk to any other place, right. That is what a planar, like that is your notion of planar connected graphs. No? If you start from any point in the graph, you should be able to walk to anywhere in this graph. So, I will sort of try to do that in a geometric setting where you have a planar subdivision, and I would be able to, by storing this planar subdivision in this doubly connected edge list in a certain way, so that I am able to walk from anywhere to anywhere, and in that I would try to minimize the amount of storage that you do. Okay. So, what I have is edges, rather I have vertices. So, I will keep records for, vertices, edges and faces. So, say in your walk you have come to a vertex, right. What you now would possibly want to do is to try to get out of this vertex to go into an edge, then from there to possibly a face, so on and so forth. No? Okay. So, what I would, the record that I would keep for a vertex is I will store obviously its coordinates, right. So, so for the vertex record would be all these vertices that you have, say all these Voronoi vertices you have, maybe some n many vertices. So, for each vertex I would store its coordinate, and if I have got into this vertex, I need to get a way out. So, this vertex might have edges which are going out, edges which are coming in. There can be multiple edges, right. We have seen in Voronoi diagram that for a Voronoi vertex there are many edges incident to it. So, what I will try to do is, though there is no orientation on the edges of the Voronoi diagram, I will orient them in some way. How I will tell you very soon. So, the moment I orient edges, so for a vertex there would be some edges that come into, some edges that go out. So, for a vertex I will store one edge which has this vertex as its origin. Okay. So, I will just store for V1. So, if this was your V1, I store E1 with it. So, E1 has V1 as its origin, only one I will store. Fine. So, this is what I store for a vertex record. Now, edges are those which would sort of link vertices to faces. So, I would be a little bit careful when I store edges. No, I am not storing incident edges, one outgoing edge, just it. We will see if we can work with this much of information, else we can introduce some more information so that we can work, fine. Okay. Now, mind you, okay, for an edge, say for an edge of a Voronoi diagram, no? So, let this be a Voronoi cell. I should have some way of working on this Voronoi cell, going around this Voronoi cell in this direction or maybe in the other way round. So, what I would do is I will keep for each edge. So, you can think of an edge like you had this vertex record. You can also have edge records. So, there will be for each edge E in the record, I will keep two orientations of it. Okay. So, say if you fix on this convention that I will orient the faces in a particular direction, say clockwise. So, you can think of this that I orient the faces in a clockwise direction. So, then in your vertex record store the edge E as this, the other one you store as its twin. So, this was my original edge in the Voronoi diagram. In the data structure I keep two copies of it, one such that you can use it to go along the Voronoi face in a particular direction, and you would obviously want to store its twin in a different direction. Now, mind you, if you are working on this face in this order and you want to work obviously the other face also you would want to work on this order, right. So, this for this face this is the clockwise order. So, for the other face this is the clockwise order, and in this clockwise order, as because I have oriented the twin in this direction, I can walk, right, the neighboring face in the same direction. So, that was the idea. And what I would do is so in the edge record I will corresponding to an edge I will keep this and I will keep its twin record also, fine, and I will sort of keep a pointer in this data structure which tells me that this particular thing is a copy of this one, right. So, that now why I need it. So, during my traversal I might think of walking on faces only, right. So, that means, so if I walk on faces and I am going to jump to another face, then I would obviously edge is the boundary which I want to cross through. So, say for example, for a face I know one of its edges, and then using its twin pointer I can quickly jump to its neighboring face, right. So, I can walk along all the faces now, agreed. Oh, that is for you when you write your program. I will give you the overall idea, no. So, it depends on how you implement your abstract data types, what language you write your programs in. Fine. So, this was about, there is something more. I might even want to walk along the edges, no. So, then for an edge, when I am on an edge, I should know its succeeding edge and its preceding edge. So, those sort of pointers should be there. So, what I now do is I look at a face and I keep the bounding edges there and I sort of so this was my E, this was E dot twin, okay. this is E dot origin, this is E dot prev, so this is E dot next, and similarly you have oriented edges like this, no? You have all these things. So, you have oriented them. So, for each edge you have such things. So, that means for an edge you know its twin that allows you to jump across faces, for an edge you know its preceding edge and a succeeding edge. So, you have pointers to those records, fine. So, how you keep it, as sir was asking. So, in your, so this is your record for edge E, na? So, you will have multiple such records for each edge. So, for this E you store its twin, its previous, its E next. So, similarly this E dot prev would also have some entry somewhere. So, for this E dot prev, E dot next would be E. So, all this kind of relations you can impose on it, fine. Okay. So, this was about edge, and for an edge I also store its origin. So, E dot origin. Now, what about face? Now, for a face what I do is I will again have a face record. For a face I would keep just one edge. So, this edge E. Okay. Now, I would also store for each edge E one of its face, right, the face that it lies to your left. So, this sort of would give you, the moment you store a face record here, then that, so you have these three separate records, no, vertex record, edge record, face record. Now, the moment you store this last information, then you essentially have a pointer from your edge record to your face record. So, now also in your vertex record you have one thing on your, one information on edge. So, these things essentially ties them, these are kind of pointers that ties these structures together. So, this is essentially the nutshell in which you store a subdivision that can be represented by a planar straight line graph. Yeah, that face, the face that lies to its left, no, I have oriented the edges, no. So, E dot twin will have a different face, fine. So, what now I have been able to do is I can now walk on the edges, I can jump from face to face, and if I can walk on edges I can go from vertex to vertex as well. So, I can make these transitions from vertex to edges, right, edges to edges, edges to vertices as well, because for an edge I know what is its origin, right, and I can even jump from edges to faces. So, this is kind of a very rudimentary idea. There are some more details which if you want to really write a program for storing such a subdivision, you have to be a little bit more careful, but this is the essential idea. So, this is a data structure that would allow you to represent, I mean see the diagram, the Voronoi diagram that I was showing you, or even the higher dimensional Voronoi diagram or Delaunay triangulation Arijit was showing you, this is a geometric structure, right. It was appealing to you as a structure, but really how you walk around that structure has to be implemented in your computer by suitably representing that structure using a data structure. No? Arijit was at some point was talking of some word representation of some geometric structure, no? Some intervals, things he was talking. So, essentially it is a nice thing to understand the geometric structure, that is okay for mathematicians, but for computer scientists we need to even represent that structure in some suitable data structure such that we can walk around, do certain things on that structure, right. So, this is the broad idea of a doubly connected edge list, but again this also till now does not give you, this allows you to walk on the data structure, but this does not give you still a logarithmic search. No? Given a point, you can now look at all face records to figure out which face you are in, then possibly say once you search all the faces to figure out which face you are in, then possibly if your car is moving across these faces, you can simulate the movement on your data structure now, right. But I am giving you no guarantee on quickness. I am giving you some linear guarantee that you can search things in linear time, and I have given you a representation on which you can walk, you do certain things, right. So, think of a GPS query somewhere, you have given a coordinate, I search for all faces, get into the face, and now I have a suitable data structure that can allow me to simulate a walk of your car or your cycle, fine. Now, I will try to impose on this doubly connected edge list a kind of a subdivision which will allow you to do the search in better time. So, the next data structure that I am going to talk of is, what we will essentially do is, if I get back into the Voronoi diagram thing, okay, let us start talking till he copies. So, this Voronoi diagram is given to us, and I have been able to store this Voronoi diagram in a data structure. Now, essentially what I would want to do is divide them into suitable subdivisions even, such that I will even want to divide this, say each cell into some suitable shapes such that, mind you, I am looking for a logarithmic kind of search. If I am looking for a logarithmic kind of search, what sort of search I am looking at? A binary search. No? So, a binary search can be done on something which has a order, right, some order. So, I have to in some way impose certain order on this, some greater than less than kind of order, such that I can quickly search, fine. First thing is like, well, I will subdivide them in as much ways as I can. So, what is your idea now? Throw up some ideas. Through each Voronoi vertex, draw horizontal and vertical lines, right. What will happen? So, if you are drawing through this vertical and horizontal lines, right. So, you will break them into some kind of triangular shapes, or if you are a little bit careful, maybe some trapezoidal shapes. These are kind of linear structures. So, bounded from above and below by either an edge of the original subdivision or some vertical or horizontal line above below and some lines on the right. So, now what you can do is, so your plane has been subdivided by some vertical and horizontal lines. We will even modify this a little bit very soon, but what I have been able to do is I have been able to draw some vertical and horizontal lines to divide the plane, but mind you this vertical and horizontal lines I did not draw everywhere, I drew it only at the Voronoi vertices. So, these square kind of partitions or this kind of trapezoidal partitions of the plane were induced by the Voronoi diagram. Now, I even ask you to do a little bit better. What I say is do not shoot the lines full, shoot a line above and below from each Voronoi vertex till it hits another edge of your subdivision, right. So, this will sort of induce a interval order on the x axis, kind of do a binary search there. So, you have your now point coordinate, you do a binary search there, that will quickly bring you to an x interval within which within this slab your clicked xy point lies, right. Now, because of this horizontally drawn lines also, you also have an order on this slab, no. So, again do a binary search on that order. So, this is the essential idea. So, now I will make this idea more formal, make this more technical to really make things fall in place. So, this is about, so you have this doubly connected edge list which maintains this basic structure, and on top of this you have this induced structure that allows you to really figure out your search. So, essentially what you have done is these big convex pieces you have broken up into smaller manageable convex pieces within which you can do binary search, and you store this. So, for each face record now you would store the subdivisions of this convex face as well, fine. So, now once you get into one of those smaller faces, you know which bigger face you are in, right. Okay. What I did was I had this bigger subdivision with me, and then I drew this vertical and horizontal lines. So, what it does? It breaks each bigger convex piece into smaller meaningful convex pieces. I will show you that they are trapezoids, right. Now, what I claim is this trapezoids has a nice xy order, x order and a y order. So, your clicked point has a x coordinate. So, with this x coordinate on this interval, disjoint intervals, do a binary search to get into the interval you are in. So, what it does for you is it locates you within a slab, right, x kind of a vertical slab within which your point is. Now, as because you have drawn horizontal lines, you also have an order on that slab, again do a binary search there. What it will, right, what with the y coordinate, what you will get into is a smaller convex piece. Now, just store the information that this smaller convex piece is part of this bigger convex piece. So, now you know which face you are in, good. Okay. So, this is the philosophy. Now, let us do the basics. So, the decomposition, so we are now getting into planar point location, and the decomposition that I will talk of is known as trapezoidal decomposition. The scenario is as follows. Say I have a region within which I am inserting line segments. So, now I even talk of general situation where you have line segments, right. Voronoi diagram is a special kind of division. I now even talk of a general situation. You have line segments, and that is going to induce division on the plane, and I am going to search within this structure. Okay. Assume without loss of generality that no two points share the same x coordinate. I would allow this is allowed, that there can be vertices in your input which is shared by more than one line segment, but this is like a little bit of a problematic case for me. You can handle it, but let us for this class let us forget about. So, we will forget about this situation. Okay. Now, what I do is I shoot a ray. As I said, the initial idea was to shoot rays full, but now I will not shoot rays full, but I will stop whenever I either hit a segment or hit the boundary of the big box within which all line segments lie. So, shoot a ray from here. Again shoot a ray from here. So, shoot a ray above, shoot a ray below. See, I am even considering a more general situation, right. These are just arbitrary line segments. Voronoi diagram is a special case of it, where it is a nice region. You can do the same thing on a Voronoi diagram. Again from this you shoot, right. Done. The earlier thing was like I said that from each point shoot a ray above, shoot a ray below, but then again like I am trimming it to the upper and lower line segment that I hit. Now, what I have done is, so now I have created a subdivision of the plane, right. So, this is, and each subdivision is now a trapezoid, agreed. Now, remember one thing, if I did had shoot full lines, then the searching would have been very easy. In here there is a little bit of a problem, because each one is a trapezoid, no. So, earlier if you did shoot all vertical rays full, all horizontal rays full, then given an x coordinate you can quickly figure in which thing you lie in, and then again in this slab you do a binary search. But in here the structure is not like that. Now, why did I shift from this one to this one? Because in this your number of cells could have been huge, no, kind of have got to n square kind of thing, no, because you have n vertical lines and sort of n horizontal lines, they might end up producing order n square cells, and some of the cells are really redundant. So, that is the reason I did shoot it this way, fine. So, but in here also I have created many trapezoids, no. So, let us see what is the number of vertices that I have. In that the existing vertices I will also count, and the newly created vertices I will also count, fine. So, your first lemma is, can you see this color from the back? Yeah. So, number of vertices, let us figure out what it is, number of trapezoids, let us figure out what it is. All such vertices that you need to, yeah. What else can it be?
So, there is a general setup and the lines are drawn, and if you for any general kind of arrangement of the lines, if you draw that shoot line vertical,
It will be quadrilateral, no? And this is okay.
always achieve with trapezoid.
Surely, right. It will be bounded by one segment from above, one segment from below, and the other left and right things are vertical lines only, no. So, they are parallel, right.
If it is horizontal line, it is a rectangle.
If it,
If there is a horizontal line,
then it is a rectangle, but a rectangle is kind of special trapezoid, right. And that is the reason I made this, you can sort of move around a little bit and then see. The point is, when you study geometry theoretically, try to keep this away. I mean, then it is like it sort of disallows you to appreciate the algorithmic content of it. When you write programs, when you really go to implement it, this sort of things you should take care. But the catch in geometry is this sort of boundary cases, or this sort of, what should I say, this the ones for which I take these assumptions to get rid of this, sometimes it affects the theory as well. Those are the situations when you should be very careful. If you remove this general point assumption and this, sometimes, rarely, but it affects your theory as well. But in most cases you can get around this. Okay. Fine. So, let us count the number of vertices. Quick, 6n, right, because for each vertex you shoot a line above, below, it goes and creates 2 new vertices, and you have this one. So, per segment you have 2 vertices. So, you have 6n and include this 4, right. So, linear, the number of vertices that you have created is linear. So, this is no longer a question for us. Okay. Now, let us look at the trapezoids. What is the number of trapezoids? How do you count trapezoids? Now, this is a, now see, in combinatorial counting, essentially what I am trying to do, I am trying to count a geometric object. This is kind of a very easy counting as compared to what Arijit was doing in his last lecture yesterday. Remember what he was doing? He took a vertex, sort of oriented the edges up and below, then he said at least n by 2 here, and then he was looking at the faces incident to this, and he was sort of counting the number of faces to fix that bound. So, the essential idea was that I am to count the combinatorial complexity of a certain geometric structure, but I cannot get a good handle over it. So, what I will do is I will look at another geometric structure which is easy to count and sort of relate it with that. I will count this, that would fix the counting of there. So, in here what I do is I look at a trapezoid and I look at its defining vertex. Okay. So, for a left vertex of a line segment, now look at a line segment, right. I have disallowed this vertical kind of line segments. So, look at a line segment, look at its left end point. This yellow color, can you see from the back? No. No. Okay. Yellow is not good, red is good. Okay. So, look at a vertex, look at a left vertex of a line segment, right. To it I will charge, rather it is responsible for creating these 2 trapezoids, right, because it did shoot a ray up, shoot a ray below, and there was a segment going through it. So, it must have created 2 trapezoids, that is 1. So, in here you have 2, and the right segment of it would create 1, right, because when you are on the right segment, there is no one obstructing you from the right side, it ends here. So, if you shoot a ray above, then for this trapezoid, this is the left defining vertex. So, what essentially I do is for a trapezoid, I sort of transfer my charge to my left defining vertex. So, each trapezoid sort of transfers its count to its left defining vertex. So, now each line segment, if you now come back to the line segment and look at its vertices, each left endpoint has got a charge of 2 and each right point has got a charge of 1. So, in all you have 3 n line segments, sorry 3 n trapezoids and a 1 for the extreme one, right, because this has been created by this one. So, this is 3 n pi. So, the story from here is the combinatorial complexity of the structure is linear. So, what each trapezoid what it does? It transfers its charge to its left defining vertex. See this look at any say, such a trapezoid. This is defined by what? Only this vertex. This vertex is going to be responsible for only one trapezoid to its right, but this vertex is responsible for 2 trapezoids to its right.
Just see the line, the line, the blue line you have drawn.
This, this,
Distance.
yes. So, this is responsible for this and this. This is responsible for this. What above? No, this, no. This will come from somewhere else, no. This will come from this. So, do not confuse among vertex and trapezoid. What I am doing is, I am trying to count trapezoids, but for each trapezoid what it does is safely transfers its responsibility to its left defining vertex. Now, just look at the vertices and count the number of charges deposited at each. Fine? Okay. This was a general argument, no?
How do you generalize, because in this case you got 3 plus 1.
3 n plus 1.
3 n plus 1, but in any other case that might be that this should not come to.
This is an upper bound, no? In some cases this might even be less, but this cannot go over this. That is what I proved. To each vertex, what is the charge that can come, no? Only through its defining trapezoids. Fine. That is what I said, no? To each vertex, these 2 charge. What are the charges? The number of trapezoids that this vertex has created, right. So, I am not left any trapezoid. Okay, so, convinced that the structure is of linear size. Now, notice also another fact here which will sort of take us to a most repeated theme over a few days of randomized incremental construction. In whichever order you insert these line segments, the final trapezoidal decomposition is the same. You appreciate this fact? In whichever order you insert, right. So, essentially what I have to show you is, when you insert a new line segment, it might be so that you have to trim some other things, right, but the structure is essentially depends on the set and not on its order. Yes, now what is your question? Plus 1 is for the last one. See, I am what? No, see, everyone is transferring its charge to the left, no. So, think of this vertex where its charge is getting transferred. I mean, if you really don't bother about this one, some 3 n plus some big O of 1. Are you happy? The essential thing I want is that this structure has to be order n, linear. Fine, but my counting was correct, I know. This is essentially 3 n plus 1. Okay. So, now comes a new now this new line segment is created. Now, this new line segment is created. Fine. What I have to do is, now slowly I am taking you to this randomized incremental construction. So, you have inserted I lines, this was your structure, and if you had inserted I lines, you are sure that the combinatorial complexity of this is order I. Now, you have inserted the I plus 1th line. What do you do? First, you have to figure out the cell of the trapezoidal decomposition within which your left end point lies, because this would get split in some way. Similarly, then what you can do is possibly, mind you, I have this doubly connected edge list stored with me. So, if I can think of a walk along this line segment, that would be jumping from this face to this face. So, this I can do. So, I can sort of walk along this line segment on the facial decomposition, fine. That is the reason I put this doubly connected edge list for you. Now, how do I locate this point in this decomposition? You know, essentially I was building my data structure to answer point location queries, but you know, do you appreciate this kind of this chicken and egg problem here? You are in a circular logic, no? I was trying to build up a data structure which would allow point query, but look here, to build this data structure I need such a thing. You appreciate this problem of this? Okay, assume you can do it. Assume you can do it to, I will sort of later on show you how you can do it, but assuming that you can do it, what you can now do is, you can shoot rays above and below, because you know for this trapezoid what is its upper bounding segment, what is its bottom bounding segment. So, this will sort of divide this cell into two parts, done. So, this is the new trapezoidal decomposition. So, what happens is, the earlier bigger one, this was the earlier bigger one, this now gets split as this, this and this. So, those of you who had doubts about your counting, now see, this did create one here, this did create another here, no. So, 3 is the new creation at most, fine. Now, what I do is, this cell has been taken care of. Now, I do this walking along this line segment, okay. I get into this trapezoid. So, I am getting into this new trapezoid. So, this new trapezoid is being sort of pierced by this line segment, right. So, it breaks up the original trapezoid into two parts, this and this. So, I had this, this, this. Again it pierces through this two, again you break up, again this pierces to this, this you break up, and then it ends here. It is easy to find, no. There again here you do not need to do a logarithmic search to figure out that it ends in this cell, because here you cannot walk past any further, fine. Here what you do is shoot a ray above and below, and create your new trapezoids. So, this is your new subdivision. Now, see, in doing so, what you have to do? You had to trim some of the existing bullet shots, no. Consider this bullet shot. This was there for an earlier end point of a line segment. So, this was there, but this line segment has to be trimmed by this vertical line segment which you did shoot earlier, has to be trimmed by this newly inserted line segment, right. So, you have to trim it appropriately such that what happens now, you see this part will go off, right, and this part has to remain, fine. Okay. So, you have to do accordingly, right. This part goes off, but this part has to stay. So, similarly here also what you have to do, look at this entire bullet path and trim it accordingly. So, here this thing should remain, this should be there and this part should go off. Similarly, here this part should be there and this part should go off, right. Now, is my drawing correct? Right. So, I have got all trapezoidal decomposition. So, when you hit, so what are your essential things that you need to do for the left end point? Figure out the trapezoid that you are in, takes some time, we will figure it out later, but once I get into that phase I can walk on this line segment to get to its end, but while going so I am hitting many earlier short bullet paths which I have to trim appropriately, fine. This will create some new trapezoids. Now, you obviously appreciate this fact that in the worst case, if you had earlier I lines inserted which had induced for you order I subdivisions, this I plus 1th line might disturb all of these order I things. There can be a worst case scenario, and like in all kind of this incremental construction, your worst case might blow up to n square summation of order I. But again you have appreciated this fact that in whichever order I might have inserted this, the final structure is the same, right. And if you agree to this counting that I did earlier, no, this earlier, so then when you have inserted I plus 1th lines, your number of trapezoids is order I only, no. It might have disturbed a lot in this, but then your previous things must have disturbed some very less. Now, we will settle this in a nice way. So, what we will show next is, we will break up for now. So, what we will show next is after, so next Orithro will talk of some data structures, some geometric data structures, and when I again come back in the lecture before lunch, I will do the analysis of this and I will show you that on the expected case, like see this is the common recurring theme. When you do this incremental construction for Voronoi diagram, right, you insert a point and then you know that the disturbance around in the expected case is not much. Here also I will do the same. I will show you that the expected case for the disturbance for one insertion is order 1, fine. That is what I will show to you, and I will show to you that this search is kind of logarithmic, right. So, on the expectation the disturbance is order 1, logarithmic search for each one to locate its left end point, you have n such line segments. So, roughly I would expect a n log n kind of construction time for creating this subdivision, and what I mean for this to go through, really I need to show to you that you can locate this point in logarithmic time. But mind you, till now I have not shown you, like say I had this Voronoi diagram, right, this was a geometric structure for you. I brought in a doubly connected edge list which was a concrete data structure that supports this subdivision. I have till now not shown to you a concrete data structure that supports this subdivision. Now, what should that data structure be like? So, this data structure should be like what now I have? I have trapezoids, no. So, a trapezoid has a left thing and a right thing. These are vertical lines. So, these are just x coordinates, fine. Now, the problem is to give me an x coordinate, I can quickly do a binary search to figure out which interval I lie in. But in here the problem would be these intervals kind of overlap, no, because if you drop them they sort of kind of overlap. So, you really cannot play this game very straight away by just doing binary search on x axis. So, what I have to do is I have to develop for you a data structure that has these segments as well as left endpoints in some way, so that given a point you can, I am not talking of this logarithmic search. So, given a point you can quickly figure out that what is the x extent and what I am below, what I am above. So, this data structure would not be a kind of a binary data structure, it would be kind of a directed acyclic graph such that some of its nodes would be these segments where you have to take a above below decision. But the point is, when you have to take an above below decision, your data structure should ensure that you are within this zone only, right. See, a left right decision on a vertical line segment is easy to take, but if you are asked that I want to determine whether the point is above this line segment or below this line segment, then it does not make any sense to look for a vertical slab which is away from this vertical slab induced by this line segment. So, your data structure should be such that it has these segments and these vertical lines placed in an intelligent way, and it would be kind of a directed acyclic graph such that you can do this search intelligently. So, I will start in the lecture preceding lunch on defining for you a data structure that essentially supports this subdivision, and once I have been able to do this data structure, then I will show that this data structure on the expected case would support a logarithmic query on a query point. But mind you, there is also a problem. The analysis that I do is on an evolving data structure, no. I am inserting lines and I am building the data structure. So, most of the analysis that you have done is your data structure was fixed, and then on that you did kind of a randomized analysis, no. Skip list is one such data structure. So, your data structure is first fixed and on that you analyze, but in here the data structure is evolving. So, what I will do is I will take a fixed point and I will argue on any random order of the insertion. Okay. So, this would be kind of an involved and kind of a nice analysis. So, which I will do in the lecture preceding lunch.